Yeah, thanks very much, and thanks for the invitation to come and speak. And it's a real pleasure to be here. And I really enjoyed seeing the space. It's really remarkable what you guys have here. It looks really nice. So I'm going to talk to you about affect, and so essentially that means emotion. And I'm going to talk to you about how emotion is important for intelligence. And I'm going to try to make the point that, in fact, emotion is one of the key motivational factors that humans use when interacting in groups. So it's one of the things that we use primarily to govern the way that we interact in teams of people, and it's something that bonds us together and allows us to work more collaboratively together as human beings. And I believe that if we design artificial agents that pay attention to emotion and actually use it in order to be members of a socio-technical system, then we can build artificial intelligence that's much more effective at becoming really a member of our modern society. All right, so here we are in the Vector Institute. So everybody here is interested in studying artificial intelligence in some way. And of course, as we all have seen, we've made tremendous advances in AI over the last couple of decades, and certainly recently things have really taken off. And here I have a couple of just a mishmash of a few sort of key examples throughout history, from computers that play chess and beat grandmasters to Go playing computers now, and self-driving cars. But when you look at how artificial intelligence works in groups, the situation looks a little bit different. So here we have the sort of maybe the canonical example of a group artificial intelligence, and the robot soccer competition. And so this video was taken from 2017, and these robots are in a team, so they know where these other robots are, and they know that if they kick the ball or whatever things, they can operate as teams, but they don't have a sense of the team as a whole. They don't really know what bonds them to this team, right? All they know about is their goal of putting the ball in the net. So really artificial intelligence lacks this glue that humans use to bond us together, which is empathy, altruism, culture, and emotion. And there have been some attempts to put emotion into robots. So like, for instance, this fellow here who's looks happy and then not so happy. Maybe he let a goal in. But of course, these are just scripted behaviors, and this robot has no idea what it's doing, and it's not using this as any kind of communication device. And this is quite different if you look at human teams, and this is the under 13 Barca team, which just defeated this Korean football team. And you can see this vast array of emotions going on in human soccer players. Including this guy who's doing this, I guess it's some kind of Spanish expression of condolence, which is slap somebody on the cheek. So, anyway, so really artificial intelligence lacks this ability to understand other beings at that level that we humans do. Okay, and this is fairly well known. So we can see, for example, with the self-driving cars, have major problems when they come to busy intersections, for instance, because they get stuck. They can't display the right amount of aggression in order to get through the intersection, right? And this amount of aggression is a cultural thing. So it's something that's shared within the culture that people understand. So this cartoon by the Oatmeal sort of lampoons this and shows this human and this car trying to negotiate passage through an intersection, and the human saying, oh, what if I point and flail my arms around, and the car is completely confused by this, right? So the problem is that the car has no idea how a human being works, right? And I'm sure that you've been in a situation like this where you're trying to figure out who's supposed to go first, and it really is a sort of a dance of some kind of aggression, right? I'm just going to force my way into the intersection, and you're going to wait, right? And everybody is able to kind of play that game in some way because we understand each other on this emotional level. So artificial intelligence, we have had lots of attempts to bring emotion into AI. I don't know why I put von Neumann here, but anyways, he's a big founding figure in AI. Herb Simon was probably the first one to really start thinking seriously about what emotion does in human intelligence. So as the sort of one of the pioneers in cognitive science, he described emotion as something that disrupts cognition. So here we are thinking all our big high-level thoughts, and then we have this emotions that comes in and sort of wrecks everything. And then we have Roz Picard, who wrote the book on affective computing, so coined the term. And this was one of the opening, this is the opening line of her book, Affective Computing, in 1997. This book proposes that we give computers the ability to recognize, express, and in some case have emotions. Is this not absurd? And in 1997, that really was thought to be completely absurd, but as an MIT professor, she could say these things and get away with them. But now it's really taken off, and there's an IEEE transactions on affective computing. There's a couple of major conferences. And Roz Picard gave the opening keynote at AAAI in 2017, and she discussed some of her amazing work at wearables that detect emotion and their applications in healthcare. And really, these things have been quite revolutionary. One of the things she said, though, was she said this, emotion and affect plays a major role in artificial intelligence research. And I looked through all of the titles at AAAI that year, and the word emotion did not appear once. I looked for affect, social, nothing, none of those words appeared, right? So in a sense, maybe it's true, maybe we were almost there, but it's sort of been pushed aside by a lot of the recent work in artificial intelligence that has sort of really ignored the affective computing domain. Feel free to interrupt anytime. Okay, so what's really going on here? This view of Herb Simon, which was emotion is something that comes in and kind of disrupts things, I think is actually fundamentally wrong. Okay, and I'm going to try to explain why that is. First of all, maybe the biggest piece of evidence we have that it's wrong is the neurophysiology of the human brain. And so this is a very highly stylized picture of what's going on in the brain from this paper by Zhu and Thygard. And it shows these two pathways, a low road and a high road. All right? The low road is something that happens very quickly, is a cognitive process. So this is not a sort of knee-jerk reaction. It's not something like that. It's actually a cognitive process, but it delivers sort of reasonable quality, very fast solutions to problems, specifically problems when people interact with other human beings. And then there's this high road that comes in after the fact and tries to sort of adjust and make up for things. All right? And in general, it's thought that this high road is only really used when the low road fails, right? So the low road is this emotional reasoning engine that humans use just to get along with each other. And then when that breaks down, then people have to resort to this high road. So you see the same idea across a wide range of different disciplines, right? Maybe the most famous is what I guess it was popularized by Daniel Kahneman in this book, Thinking Fast and Slow. And these two terms there, the high road and the low road, were termed by Stanovich and West, who were two economists, as System 1, which is like the low road, and System 2, which is like the high road. And really, when you read about it, the way they describe it is that when System 1 runs into trouble, it calls upon System 2. So again, there's this same idea. This is interesting to the economists because people will tend to make economic decisions based on their System 1 thinking, right? And the idea is that, no, you really should reason about the economics of your decisions and make sure that you call into play this System 2 thinking. Okay, so here's the sort of generic view of affective computing that I think really pervades all of the research field. You take the sort of classic view of artificial intelligence, which is we perceive something about the environment, we have some cognitive processes that are reasoning about what's going on, and then we deliver some action back into the environment. And then these emotions are things that are happening kind of on the side, and then they're sort of coming in and sort of wrecking everything, right? Or disrupting things in some way. And the disruption may be useful. We may be able to characterize it in some useful way, but it's really like a secondary process. So really, that's affective computing. A lot of affective computing considers this to be a cognitive machine disrupted by emotion. I believe that it's actually fundamentally the other way around. What happens is the first thing is this low road. People use an affective reasoning engine in order to figure out what to do next. And then, if necessary, these higher level cognitive processes are called in order to correct for any mistakes that are being made by the affective reasoning engine. So really, I believe that we're dealing with an emotional machine which is disrupted by cognition. So it's fundamentally the other way around. Yeah.
So sometimes, like when I decide things, right? Like I don't know, right? Like sometimes it's just I use the affect, right? Like, but sometimes I use the cognition, but then sometimes the cognition is not enough.
Mm-hmm.
So ultimately, in those borderline cases, do you think it's the affect that drives the decisions, or?
So I think affect is a big part of human motivation to act. It's actually the thing that drives you to take action. Without affect, without these affective processing systems in the brain, people don't act, right? And that's sort of fairly well known. A lot of this stuff happens up in the frontal lobe, and if you remove those parts of the brain, then people become unable to make decisions. They can still do all of their reasoning. They can write out they can do all their mathematics, they can speak fine, they can do everything just fine. They just can't decide what to do, right? And so I really think that's what is the final sort of the thing that drives you to actually do something is this affective processing. Okay. So I want to now try to describe how we can build this kind of a model as a computational machine, okay, as a piece of artificial intelligence. In order to do this, I'm going to look back at the work of this psychologist Osgood in the 1950s. And Osgood did these remarkable experiments where he went around the world and he asked people to rate concepts, so in this case the word polite, on a number of semantic differential scales. Semantic differential scales are just scales with opposing adjectives at each end, like angular to rounded, weak to strong, rough to smooth. And what he found was that people that share the same language, people in the same culture, have this remarkable degree of consistency in how they rate concepts. So here you see two groups of 20 people rating the word polite on these semantic differential scales. This is from Osgood's 1952 paper, and you see this in the mean of these two groups of 20 people, you see this amazing consistency. So what's going on here? We have this politeness, and then you look at these semantic differential scales, and you think, well, what does politeness have to do with something being rough like this carpet or smooth like this table? It doesn't have anything to do with it, right? And yet everybody agrees that politeness is kind of more smooth than rough, right? So Osgood, he didn't actually just have this set. He had a much larger set. There was around 150 or so semantic differential scales. And he came back and did some dimensionality reduction and found that he could account for over 80% of the variance in all of this data using just 3 very simple dimensions. And the dimensions are a dimension of evaluation, good to bad, power or potency, strong to weak, and activity, which is like hyper or asleep. So I'm putting this coming out of the board. So bigger things will be more active. So we can put our emotion words in there. So being polite is sort of good and strong, and being abusive is sort of very bad and a little bit weak, right? The key thing is that everybody that you ask will agree. You say polite. Put a point in this 3-dimensional space where you think polite is, and everybody will agree it's roughly in the same spot. We can do the same thing for behaviors. So these are behavior words in red and identities in blue. So students and professors are about the same goodness level. Maybe professors are a little bit more powerful than students, and maybe students are a bit more active than professors, right? They tend to be younger. So that's kind of. And this is culturally dependent. So if you go to Japan, for instance, the professor-student differential on power is significantly bigger. Whereas in North America, students and professors have sort of become normalized, and we're all more equal in some way. Okay? Okay, so again, the point to remember here is that everybody shares where these words go in this space. Okay? We all have this knowledge embedded in us somewhere. So how do we turn this into a control mechanism? So I'm going to now explain to you affect control theory, which is a very simple mechanism that leverages this shared sentiment in order to give us an affective motivation, affective policy, essentially. What do we do next? All right, so I'm going to step through affect control theory in a couple of layers of complexity. So going from a very simple description and then a little bit more complex, then try to give you the full model, which is not very complex model. So here we have our fundamental sentiments. This is what I showed you on the previous slide. So this is how we all agree on where things go in this three-dimensional space. Okay? When we see something happening in the world, a social action, so maybe a nurse maybe helping a patient, or in this case a nurse pouring a bucket of water on a patient's head, then this creates what are called transient impressions. So things change when we see the interaction of concepts, right? Nurses comforting patients is different than just a nurse all by herself. And the difference between these transient impressions and the fundamental sentiments is called the deflection in affect control theory. And the control principle is that people try to reduce this deflection. Okay? They try to experience events that confirm their fundamental sentiments. So it is an emotional consistency theory. We as humans try to seek out situations in which things come together in an emotionally consistent way. And that emotional consistency is also something that is culturally shared. So it's described, a lot of this theory was developed by a sociologist by the name of David Heise, and it's described in this really nice little book in 2007 called Expressive Order, which sort of sums up a lot of the research that was done. But this is the sort of one of the summations of like 30 or 40 years of work on this theory, and a lot of validation of it. Okay, so how affect control theory works is it describes events in the world using a really simple grammar of actor, behavior, and object, where the object is usually another person, another agent. We have our fundamental sentiments, which are a three-dimensional vector for each of these three things. So that's a 9-dimensional vector. And it lies between minus 4.3 and 4.3. And I've asked every sociologist I know why it's 4.3, and I still can't get a good answer. It's buried in the sands of time and somehow related to those experiments in the 50s that were done. But really, you can rescale this to be anything you want. 4.3 is not important. We have our transient impressions, which are, again, a three-dimensional feeling about actor, behavior, and object when they are seen in context. So that's another 9-dimensional vector. We can predict these transient impressions from the fundamental sentiments using a linear operator, which I'll show you in a second. This is also something that we can measure empirically and something that is culturally shared. The deflection is then the Euclidean distance between fundamentals and transients, and the affect. And this deflection defines an optimization surface that we can walk down. We can say, well, how are we going to get to something of lower deflection by optimizing over this function. The affect control principle, like I mentioned, is that actors work to experience transient impressions that are consistent with their fundamental sentiments. So what they do is people will seek out situations in which there is this emotional consistency, so in which deflection is low. If deflection is not low, then people will try to re-identify things, re-interpret the situation, or will try to take action in order to optimize or minimize this deflection. Affect control theory is, I think, the only theory I've ever seen where there is a precise definition of what emotion actually is. Emotion in the theory is described as being proportional to the vector difference between these fundamentals and transients. So what it is, emotion is a communicative signal. And it allows humans to relay how they're feeling. So if I'm interacting with somebody and my transient impressions are distant from my fundamentals, I can say, I can compute what that vector is and send it as a communication to the person I'm interacting with. And that communication is telling that person, here's the direction you need to go in order to fix this up, right? Because it's not working for me. Okay, here's a nice pretty picture of all this. So here's our social interaction. We have our nurse interacting with our patient. Here we have our symbolic interpretation of that in terms of these labels. So nurse comforts patient in this case. We have our fundamental sentiments, 3 dimensions for each of these 3 things. We have our impression formation equations, which is a linear equation with some nonlinear features or some polynomial features in these fundamental sentiments. And these coefficients are things that we also measure by asking people questions. So this sentiment dictionary over here contains all of these ratings. It also contains these coefficients. So we've measured these as well. This yields these transient impressions, and then we can compute this deflection, what emotions are expected, and also which behavior we expect to see next. Okay, so we can validate this by looking at the data and seeing whether it does predict what comes next, or we can bake this into an artificial agent and allow it to decide what to do next. And the decision is the behavior that's going to minimize or optimize over this deflection function. Okay, so let me walk through an example, unless there's any questions about the basics. Yeah.
Does the behavior always evoke the same emotional manifestation in the patient?
So yeah, in the same situation, it would evoke the same one. Yeah.
Because you can imagine 2 very different people
Mm-hmm.
for whom you perform the same action that interpret it very differently and
Right.
register it differently.
Yeah. So this sort of relies on the nurse being interpreted as a nurse and the patient as a patient. Now, the patient may not feel like a patient, right? And in a lot of the work I do in Alzheimer's care, this is a major issue because the person doesn't think they're a patient. They think that they're a lawyer, right? And so a nurse comforting a lawyer would give you a very different set of impressions and a different deflection,
Exactly.
right? Yeah, absolutely. So as soon as there's a disconnect, so this relies on the nurse believing that she's a nurse and the patient believing she's a patient, and the patient believing the nurse is a nurse and the nurse believing, right? So it all has to be, all on the same page. As soon as there's breakdown, then then you can get different effects. So, yeah.
How do you reconcile new situations? Like, according to this, could you ever be surprised by your emotional response?
By your own emotional response? Essentially what that would come down to is a conflict between your cognitive interpretations of things and your emotional reactions to them, right? So definitely, this all starts with a symbolic interpretation. So I'm in a hospital, somebody comes in the door and they're wearing a white coat. I say, oh, doctor, right? And that word doctor then evokes this sentiment about doctors that I have, and then that sort of leads to whatever comes next. But if that person coming in, let's say, was not a doctor, right, was the janitor or something, right, for some reason, then their behavior in response to me would create an awkward situation, right? Maybe the opposite would be a better example. So I think this is the janitor, but really it's my doctor, right? And I sort of maybe don't treat this person with the right amount of deference for a doctor, then the doctor gets offended, and then there's a big breakdown that happens, right? So you can easily get confused. This theory is really an equilibrium theory. It works well at the equilibrium and for small deviations around it. So, yeah.
So can you just explain again about the transient impressions and the fundamental sentiments, like the difference there is what's considered emotion here? I didn't quite understand that.
Okay, so the fundamental sentiments create these transient impressions, right? And the vector difference between these two gives you the emotion. So this is how the nurse is feeling about being a nurse, right? And this is how the nurse is feeling in this particular situation, right? So in the situation where the nurse is comforting the patient, this is going to make the nurse feel really nurse-like. This is what nurses are sort of expected to do. So the difference between this transient impression and this fundamental is going to be quite small. And the emotion that's created will be the characteristic emotion for a nurse, right? Maybe something like an emotion of compassion, right? Or something like that. And then she would relay that emotion to the patient in order to express the fact that I'm feeling just like I'm supposed to be feeling in this situation, right? But as soon as there's something goes wrong, and I'll show you an example in a second, then this transient might be very far from the fundamental. The emotion will be very different, and the relayed signal will be something telling the patient, I'm not feeling right about this, right? So, and not only that, but here's sort of what you could do in order to fix it up.
Okay, so
right?
there's like no such thing as like an emotion that like someone would like feel all the time. Like it's always defined as like a difference from that.
Yeah.
Just clarifying.
Yeah, well, yeah. I mean, it's when everything is all well aligned and you're right at that equilibrium point, then you get a characteristic emotion, which is sort of like, this is what you should feel like in this situation, right? So if I'm a depressed drug addict, then my emotion would be sort of sadness and let's say sadness, right? And that sadness is my characteristic emotion. That's how I feel when I am perfectly aligned as someone who's depressed, right? Yeah.
I'm not sure if this question makes sense, but is the sentiment dictionary here static? So it's always the same numbers that you get for a nurse or for comforts or for patient?
Yeah.
I think that's kind of related to. Okay,
Yeah.
so then if I'm somebody who a doctor saved me before, as opposed to somebody who a doctor actually like made a mistake with
Yeah.
before, then you can imagine how my emotions would be very different
Yeah.
when seeing the doctor.
Yeah.
How do you kind of manage that?
Okay, so I'll get to that in a second. So yeah, let me come back to your question. All right, so let's run through an example. So here we have our nurse and our patient. And remember, this is at the sort of equilibrium point. So the patient thinks that she is here and thinks the nurse is there, and the nurse thinks she's there and thinks the patient is here. This is all real data taken from a survey that was done in the USA in 2003. And so you can see these ratings are the mean of those of that survey of people at that time. So the nurse is quite good, and maybe the patient is less powerful and a little bit less active than the nurse. And so if we make the nurse, so we say what happens if the nurse comforts the patient, then the deflection is very low. I've put the transient impressions in light blue, which are very close to the fundamental sentiments. And the emotions that are predicted are things that are sort of characteristic of this situation. If we make the nurse ignore the patient, right, which is something that we would not really expect nurses to do, then the transients are very far from the fundamentals. The deflection is very high. This is a situation that people will find really awkward, right? The nurse is seen as significantly more bad. So we're like trying to interpret this in some way. Who is this nasty nurse that's ignoring this patient, right? And also the patient is more bad because we're seeking some kind of consistent explanation for this. So maybe it's the patient that's bad. Maybe the patient did something really bad to this nurse, right? And the patient would feel indignant, like, how dare you ignore me? And the nurse would feel agitated, okay? Okay, so this would be a breakdown. Here's another example. This is a student and a tutor. So this is one of the first applications we built of this. There's the student and tutor. And then we can ask questions like, what would a student do to a tutor? Okay, so we can optimize. We can take a derivative of that deflection function and then solve for the best action. And we find the student would do something like ask the tutor something. What affect control theory predicts is a three-dimensional vector. Okay? It does not predict the label ask. We have to look that up in the dictionary. And so I've chosen this one as one that's close to the three-dimensional vector that's predicted, and that also sort of makes sense in this situation. Okay, so everybody's feeling contented. If we make the tutor yell at the student, then we get this large deflection, student and tutor. And so the deflection is now very high, and then we can ask what would the student do in response, would listen to, and then the tutor would apologize to and try to restore these transient impressions back towards these fundamental sentiments. and the deflection is dropping again as they do these restorative actions. Yeah.
Do you actually sort of specialize these with respect to what you're asking about or what you're apologizing for? Because in some sort of a purposeful environment, it seems to make, I can imagine it has a different effect.
Yeah, absolutely. Yeah, I mean, all of these are all of affect control theory works just in this three-dimensional space, right? So you have to always keep that in mind. There's also all of this actual context that's going on that would have to be taken into account, right? And I'll show you when I look at Bayesian affect control theory, that's where we try to take that into account as well. Speaking of which, all right, so the work that I've been doing is, of course, and this is the point that you were making before, was that these sentiments are not just points, right? Everybody doesn't agree exactly on where they are. We agree in the mean, but there is actually a fairly large variance around the mean, and that variance turns out to be really important, okay? It's related to the diversity of the culture that we live in, right? So there's a whole spectrum of research on trying to understand this, right? So the more diverse the culture, the bigger this variance gets, okay? So we won't go into that, but I can certainly talk to you more about it in detail. So Bayesian affect control theory, essentially, it's the same idea at its core, except now all of these sentiments for identities and behaviors are now probability distributions, which I represent as sets of samples, so they can be multimodal if you'd like, and they can have a variety of different forms. I also add in external goals and planning. So this is where we get to the fact that actually what's going on is a real situation, and two people are trying to interact with one another and do something. And so the Bayesian affect control theory puts that in and bakes the whole thing into a single Markov decision process. The affect control principle in this Markov decision process guides the selection of action. Okay, so it's like a heuristic or oracle that says this is roughly what you should do next. All right, and we'll go into that in a little bit of detail. So I have a paper in Artificial Intelligence in 2016 and another one in the American Sociological Review, which gives the sociological impacts of these things. All right, so I'm going to run through this fairly, let's see what time it is here. Okay, so partially observable Markov decision process, we can represent it like this as a decision network. So we have a set of states which are latent, so we can't observe them directly. And then we have a set of observations which we can observe directly. These are the things we get out of the environment. And they're related to the states through an observation function, which is a probability distribution. The agent has a set of actions available to it which change the state of the world according to some transition function, which is another distribution. And then we have a reward function, which, just to simplify, I've put here as only depending on the state. And this describes the agent's preferences, right? What it would like to do in terms of a utility function. Right, so what do we do with one of these models? Well, the simplest thing we can do is we can take the state that we're in currently. So since this is a latent space, our state is a probability distribution or a belief state. So we can start from our current state and we can build out a big search tree and say, well, what are all of the things that the agent could do next is this first branching factor, and that leads us to a new belief state. And then all of the things that the environment could do next, which is, what this other, like if we're interacting with another agent, what this other agent could do next is this next branching factor, and so on, okay? And so we can roll out this tree and write the whole thing down, and then somewhere deep in this tree are these rewards, which are encoded in this utility function, and then we can propagate these rewards back up through this tree, and that tells us how to rank these, weighted by the probabilities of these things happening, and then we can rank these actions and decide which one to take. Okay, so that's just Bayesian decision theory. So, of course, the problem is that this tree is, astronomically huge, and we can't actually write the whole thing down. But we can do a couple of things in order to get around that. One is we can sort of ignore observations that are really unlikely, and we can kind of get away with doing that. The hard part is the action space. We can't ignore any single action. That's the fundamental problem. And the reason we can't is that if we ignore one action, it could be that that action leads to infinitely greater reward than anything we've seen in the tree so far, right? So this is the reinforcement learning problem. We have to guarantee that we look at every single action, all right? And that causes major problems because it means that this tree is too large to write down. Okay, so now what we're going to do is, so the plan is we're going to bake in this emotional reasoning engine as the thing that is going to guide this action selection, right? So it's going to tell us, out of all these actions that we could take, here's a subset that are emotionally consistent, ignore all the rest. Okay, so it gives us a way of attacking this action, the branching factor at that first level. So there's our POMDP again. What I'm going to do is I'm just going to, just to make this a little bit easier to explain, I'm going to add a random variable which is just deterministically set by the action. Okay? And then this effect here is the old effect that we had from the action space. All right, so what I'm going to do is I layer in this fundamental and transient, which are again random variables. So I described them, they have this distribution over them that evolves over time. I have an evolution function for the fundamental sentiment. So we can admit that these fundamental sentiments may change over time, right? That could be because the group that I'm interacting with is changing. Maybe I move to a new culture and then all of a sudden everything's different. I've got to relearn everything. So that's what that one does. My transient impressions evolve according to my impression formation equation, which is that linear equation with these polynomial features, but could be replaced with whatever you want to learn. So your feed-forward neural network, for instance. Then we have this undirected link, which ties the fundamentals and transients together. And that's this potential function, which is this affect control principle. It says we expect fundamentals and transients to be close together. Then we have this semantic potential, which links these fundamentals with the behavior that we need to take and the state space. So this semantic potential is what we called in affect control theory the sentiment dictionary, right? So these are the things that we measure. These are our feelings about things in the world. Based on all of that, I can take a distribution over these fundamentals and, given my belief state, integrate out the identity components and be left with a distribution over just the behavior part, which is this random variable here. This distribution here tells me what to do next. Okay? And so I'll give you a pictorial description of what that looks like. So here we have our connotative space. So this is our affective space. This is this three-dimensional evaluation, potency, and activity space. And on this axis, I've put our denotative space, which is actually the things that the agent's going to do in the world. All right? And so each of these actions, here they're discrete, but they could be continuous. Each of these actions has a distribution over this connotative space. This is the thing that we've measured. This is what's in our sentiment dictionary. This red line here describes our prediction. This is this pi function, which is a distribution over the connotative action space. So it's a distribution over this three-dimensional affective space. We can then project this through all of these profiles, and this allows us to rank the different possible actions that the agent can actually take in the world. Okay? So there's our denotative plan tree. This is the thing I showed in the previous slide, where we have a bunch of different options to take. This thing here is going to tell us here are the ones to take to look at, and this one here you can ignore because it's really unlikely to have any to be meaningful in the situation. Okay, so this is what happens. We have our decision theoretic plan tree describing all the things that can happen. And how I imagine this is this connotative or affective reasoning engine is like shining a beam of light down through this tree. And it's important that it's a beam of light because the agent doesn't even consider these actions that are out here, right? It doesn't need to because these are so far out of line affectively that they're likely to just lead to a breakdown in the situation anyways, and the agent will only perceive the ones that are within this beam of light. Okay? So it's an attentional mechanism. It's not a ranking measurement. It's not going to rank every single action. It's going to illuminate only those that are emotionally reasonable to take in the situation. So this is related to a whole body of work in practice theory, which I won't go into, but this quote by Pierre Bourdieu in this book, The Logic of Practice, says he describes something very similar to this called the habitus, and describes how the habitus may be accompanied by a strategic calculation, but the calculations are first defined without any calculation. So in classic Bourdieu, it's very cryptic, in relation to objective potentialities immediately ascribed in the present, things to do or not to do, things to say or not to say. So this quote sort of, to me, describes exactly what's going on here. The agent has this beam, this flashlight beam that illuminates a few of these options, and then can do some strategic reasoning within the flashlight beam, right? But just so long as there's enough time. As soon as time runs out, the agent's got to make a decision. And whichever one's left, or whichever one's the most obvious, will be the one to take. If there's really not enough time, then the agent will just take the first one, the most affectively aligned one, and it's be like, oh, I'll just cross my fingers and hope this works, right? And that's essentially how people operate in social situations, I believe. Okay. So I'm running down on time, but any thoughts or questions about that? I'll run through a really simple example to show how it works, and then I'm going to talk a little bit about the Themis project. Okay, Prisoner's Dilemma. So this is a game that we did a lot of experiments with in getting people to play Prisoner's Dilemma as the Prisoner's Dilemma as the sort of minimal working example that has a cognitive component, which is I'm trying to win, and an affective component, I'm trying to cooperate, right? And so in the Prisoner's Dilemma, this is a simple description. You have this pot of gold, and you have two choices. You can either give 2 coins to the other person or take 1 coin for yourself. And the other person has the same choice, and you make your choice simultaneously and then reveal what happened, right? And the normal form of the game looks like this. So there's only one Nash equilibrium, which is to defect. So always take 1. But when humans play this game, they cooperate for long periods of time. Okay? And so the question is, well, how do we explain this? All right, so sorry this is really small, but this is the game tree for the rational agent, in which the rational agent has no idea or no assumptions about what the other agent's going to play. So it has 2 options, give 2 or take 1, and then it says, well, I don't know what the other guy's going to do, 50-50 chance, and then I have my choice, and then he has his choice, and so on. And so if you just compute this, you find that taking 1 is the better action, and that's what the rational agent does. That's the Nash equilibrium. If the rational agent believes that the person they're playing with is also rational, then it gets even simpler, because then it knows that the other guy's going to take 1, and then it's really obvious. Okay, the affect control theoretic interpretation of this is quite different. So that a pure affect control theory agent ignores the utility function altogether and says, well, who do I believe I am? Well, I'm a friend. I'm playing with my friend, right? So I'm a friend and he's a friend. Well, what do friends do to friends? Well, I can compute that with affect control theory. Well, they do something with this affective signature, which I can look up in the dictionary, which is something like treating or toasting my friend, right? And then I can say, well, in the game, what are these 2 actions? I'm either going to give the person 2 coins or take 1 for myself. So maybe giving 2 is like collaborate. I'm going to collaborate with my friend. And taking 1 is like, well, I'm going to abandon my friend, right? And you can see that if friend is playing with friend, then the optimal action is much further from abandon than it is from collaborate. So this would be the right thing to do. I should collaborate. He's my friend. Of course I'm going to collaborate with him, right? let's make the person I'm playing with a Scrooge, or maybe an enemy or something like that, which is a really more negative identity. Then the optimal behavior is less positive, but still positive enough to tell me that I should probably try to collaborate with this person, right? So it's like a reforming. I'm going to try and help this guy become a better person by collaborating with him. A Scrooge with a friend, then it switches to the other side, and I'll start defecting from this person, and then two Scrooges will defect. Okay, so there's the game tree for the affect control theoretic agent, and this is sort of really simple, but this agent only has a single branch, right? Because this is for friend playing friend. This agent will never even perceive the other action. It'll never even come into his mind, right? He'll be like, it's my friend. Of course I'm going to give him two. I won't even think about taking one. It doesn't even appear, right? So the game tree is very simple. Since he's my friend, I really believe he's going to give two. And so the optimal thing is the only thing I can see, give two. And then this is for enemy playing enemy. Then it's just a long string of taking. So it definitely simplifies these game trees. All right, maybe I'll skip the details since I'm running short of time, and I do want to talk about Themis just at least briefly. So we've done a bunch of experiments looking at humans playing humans and humans playing affect control theory agents, and found that we can replicate human play to a certain extent, which is actually quite remarkably difficult to do, is to replicate human play in this game, in this really simple game using a computational agent. And we can do all sorts of things like playing with discounting and find that agents will focus more on breadth solutions than depth solutions, for instance. So there's lots of interesting results there as well. OK. Let me move on. Actually, maybe I'll stop and ask if there's any questions about this prisoner's dilemma. OK. So let me move on. I'm just going to briefly describe the Themis project. So this really gets to the title of the talk, which is looking at group dynamics. This is a project that's done in collaboration with my colleagues, Tobias Schroeder, who's a professor in cognitive social psychology at the Potsdam University of Applied Sciences in Germany, Kimberly Rogers, who's a professor in sociology at Dartmouth College in the USA, and May Nagapan, who's a professor in software engineering at the University of Waterloo. So we have this nice interdisciplinary team, and this is funded by this transatlantic platform and this digging into data challenge. And what we're interested here is looking at how people are coming together online to solve problems. And in particular, our real interest is looking at solving sort of social problems. So these guys that are developing self-driving cars that you can sort of download kits and work on yourself and do things, or people developing apps to help the refugee influx in Europe. So GitHub is a place where I'm sure everybody here is familiar with that platform that a lot of people are coming together in order to develop solutions to things. And this is a lot of software, coders, people writing software, but it's of course been applied to lots of other things as well. And you can see this astronomical growth, and there's over 20 million active repositories on GitHub now. So what is GitHub? Well, you can start a project on GitHub. You have a piece of code. Somebody can come along, join your project, check out the code, make some changes, and then do what's called make a pull request to say, here's my changes. Do you want to accept them or not? And then that person's like, yeah, this looks good. And then there's some discussion that ensues maybe, and then it gets accepted or rejected. So you might think that GitHub is a meritocracy. So if I write good code, then it gets accepted. If I don't write good code, it doesn't get accepted. But of course, it's a human social network, so that's not always exactly what's going on. And there's all sorts of social factors and emotional factors at play. So this is from the open source survey from last year. And you can see of the top 6 problems encountered in open source development, 5 of them are distinctly emotional in meaning. So unresponsiveness and dismissiveness and conflict. Okay, so there's all sorts of emotional and social factors. And in the Themis project, our interest is to study that using this affect control theory as a lens in order to give us some insights into what people are doing. So we want to understand group behavior with models that are computational, but that take these social, cultural, and emotional factors into account. And then as an artificial intelligence researcher, I want to build artificial agents that could, become members of these teams and help them to be more engaging, more inclusive, and more effective. All right, so this is a video of this is the affect control version of, affect control theory version of group simulator, it's called. And this allows us to create teams of agents, virtual agents, that interact with each other according to the principles of affect control theory. So we can actually predict what these agents will do and which agents will interact with other agents. And then there's also one agent that's usually described as the group as a whole. So people interact with the group as a whole as well. So using this, we can make predictions about what people are going to do to one another and then look at aggregate statistics of these simulations and compare them to real data. So in affect control theory, this was done originally on jury data. So they looked at jury deliberations and then modeled them using affect control theory and found that they could describe some of the same things that were going on in these jury deliberations as they saw in the simulator. Okay, we also then, within the Themis project, we're looking at sort of from the bottom up. We actually go and mine all this GitHub data and then try to do processing on it, try to understand what are the sentiments that people are expressing when they do these pull request comments. And we have a number of different data sets. So we've gathered a curated data set of EP and A ratings, so affective ratings of concepts by GitHub developers. We've built our own word vectors based on the GitHub, a larger repository of GitHub pull requests and issue and commit comments. And then we have a smaller data set where it's been rated for emotions. The different pull requests have been rated for emotions. And we've done a little bit of, so far, a little bit of work on trying to predict these three-dimensional states for these different data sets, and also some of the emotion words like positive and negative, and a few other things, which I won't go into the details here, but you can certainly ask me about it. So the idea is really to we have affect control theory in this group simulator, which is our kind of top-down view of this situation. And then we have the actual data here, the online collaborative network, which allows us to mine some of the things that are happening in the actual GitHub teams. And then we hope that these two things will fit together and allow us to see what kinds of social structures are developing and why. And then this should allow us to design interventions and build agents and also do analysis. So things that will actually change the way that these groups behave. Okay, so I'm just going to sum up in a couple of slides. Traditionally, I think artificial intelligence has focused a lot on this mapping of this sort of equation, or equating intelligence with rationality in some sense. But we really know that human beings, emotions are really necessary for intelligence, certainly in group situations. And so what I've tried to describe here is a low road that gives some kind of heuristic social intelligence that we can actually encode in a computational agent. And this encodes a social order which allows humans and maybe agents as well to work as a real society, right? So the idea is that it encodes the solutions to social dilemmas. So I showed you the prisoner's dilemma, which is this canonical one. But this cows on this field is meant to show the tragedy of the commons, which is another classic social dilemma, where the modern example is, if everybody takes the bus, we'll all be happier because there'll be less pollution. But if you guys are all taking the bus, then I'm going to drive my car because there'll be nobody on the road. But then you'll all look at me and say, "Oh, look at that guy! He's what a schmuck! He's driving his car and polluting the air." Then I'll feel all sorts of shame and terrible emotions, right? Okay, so then you might say, well, this is just because the sort of classic argument from AI is that, oh yeah, you only need this heuristic stuff because we're not smart enough, right? So if I have a bigger brain, then I could reason more about all these things and I would do better. So I believe that that's fundamentally incorrect. And if you look at theories of commitments, and in particular this book by Ed Lawler, Social Commitments in a Depersonalized World, describes 3 forms of commitments that humans make with one another. Instrumental commitments, affective or relational commitments, and normative commitments. Okay? So you had somebody here a couple of weeks ago talking about normative commitments. But I believe these affective commitments are very, very important. Okay? So instrumental commitments are if I go to a new town and there's 2 coffee shops and they're both identical and have the same coffee for the same price. I don't care which one I go in, right? I just want the coffee. And I got to give the person the money and get the coffee. So I pick one at random. I go into the coffee shop and I say, I'll have this cup of coffee, but maybe the barista says, oh, how's your day? Where are you going? Or a nice day we're having. How about those maple leafs and all this stuff? And I establish a little bit of a relationship with that person. The next day I go back and I'm faced with the same choice and I'm like, well, I'm going to go back in there because I had this nice relationship. My instrumental commitment with that person to buy a cup of coffee from him has changed into an affective commitment, right? And this is a much stronger, deeper, and longer lasting commitment than the instrumental one. The instrumental one is replaceable. If that guy moved to a new town, I don't care, I just go to the next guy, right? After I've established this affective commitment, if he moves to a new town and I'm heartbroken, oh, my barista left, right? How terrible. Normative commitments also happen, but require some kind of enforcement, right? And so one way to do this is to force it into everybody's utility function. These affective commitments do not require a utility function, right? They're, as I described before, they're like you can use an attentional mechanism to guide action selection, which is based on, which sort of encodes these relational commitments. Okay, so I have Bayesian.ca if you want more information on Bayesian, and themis-cog.ca if you want more information on the Themis project. And thanks very much for your attention.